Now let us see this, or how we use it in examples. Because the basic importance of the iteration theorem is in making calculation of double integrals easier at least. Okay, let us start with the usual, the simple example we had. Let D be the region, which is y is x squared intersected with y is x cubed. That's this region. Now, I will not have any f, because f is not important. I will consider just an arbitrary f, assuming it's continuous and so on. So integrals exist. We will not calculate that. But the idea is to write a double integral over D in terms of iterated integrals. Now, when we look at this, we see that if we look in the y direction first. So, looking at y direction. Well, y direction here means, of course, increasing y direction. Okay. We see the following. Okay, we have this picture, and at the bottom we have y is x cubed. At the top we have y is x squared. Okay, and always we move in the increasing y direction. Okay, oh well, they have to start from here, of course. Okay, in the increasing y direction, when we look in this way, we hit the cube function, first the cube graph, and then the parabolic graph. So y changed from x cubed to x squared curves. So let me better write it. Y changed from y is x cubed to y is x squared. These are curves, all right. Now, to be a simple region, the sides should be vertical. Well, actually, they are vertical. We have 0 here and 1 here. Okay? And then x changed from 0 to 1. Think as follows. Okay? We have the square graph, and then we have the cube graph. We have points A, B, and C, D. But A is equal to B, and C is equal to D. So indeed, sides are vertical. Here. Okay, y changed between two curves, and sides are vertical from 0 to 1, but the points coincide. So it is indeed a simple region with respect to y first. So D is a simple region with respect to y, the first variable. Okay. So the integral over D of f can be written as an iterated integral, where you have y first. Okay. And y changed from x cubed to x squared. These must be y equal to, because they are boundaries for y. In the meantime, x changed from 0 to 1. Okay. And if we know f, we can calculate this directly. Now, let us write the same double integral in terms of x first, if it's a simple region. Well, observe that d is also simple with respect to x first. Namely, we have the following picture then. This was y is x cubed. This was y is x squared. But now we look in the x direction. So, obviously, when we move in the x direction, we hit the region D at y is x squared curve, and then we leave it from the cubic. So, there is a first curve, there is a second curve, so x changes from x equal to up to x equal to the other curve. Well, this means that we have to express things in terms of x equal to form. So, the first one is y is x squared. Well, x is equal to square root of y plus or minus, but this is not the whole parabola. It's the positive side of the parabola. So, here I can put in square root of y because this is the positive branch, rather x positive branch of parabola. And here, I have the cubic, y is x cubed, so x is y cube root. In the meantime, y changed from constant 1 to constant 0 to constant 1. This means that with respect to x first, this is a simple region, so I can write the same integral in this form. Now x changed from square root of y to cube root of y, and coincidentally, y changed from 0 to 1. Note that if you compare the boundaries where dx comes first or dy comes first, you see that it's not a simple change of x's to y's. Not even solving for x or y. For example, this top curve, this top boundary in the first integral, if you had y here, was x squared. So you cannot write simply, well, if y is x squared, x is square root of y. No, you have the cube root. So we have some change here. Namely, note that just by looking and manipulating the boundaries of the integrals, the bounds of the integrals, one cannot change the order. Order, x comes first or y comes first, but one should go back to region B. So just by looking at these four bounds, you cannot manipulate and say, I directly write it for y. No, you have to go to the region D. Again, look at the boundaries there. This may be quite different. Okay. Now, this was an example of a region which was simple with respect to x and with respect to y at the same time. Okay. Now, a second example. Let D be the following region in play. Okay. It's the parabola, y is x squared, right? And the line y is x plus 2. Okay. And this is the region in question. Okay, now it's easy to see what the intersection points are. You can write x squared equal to x plus 2, and then you immediately see that when x is minus 1, okay, they intersect. You can even see it directly. And when x is 2, they intersect. Okay. So these are the values in question. Now, when we look at this region D, okay, we see that D is simple with respect to y first. Okay, because, of course, if you look in the y direction, you always have a first curve and a second curve, and y moves from the first curve, which is the parabola, to the line y is x plus 2. In the meantime, x changed from minus 1 to 2. So y changed from the curve parabola to the curve x plus 2. And x from minus 1 to 2. Well, this means that I can write by the theorem my double integral as an iterated integral with respect to y, the first variable, and y changed from, as seen from here, x squared to x plus 2, and x minus 1 to 2. Fine. Okay. Now, let us write this with respect to, okay, x first. Okay. Now, to write D as iterated integrals, with respect to x first, okay, well, we look at the picture. Okay. We are looking in this direction now. So, okay, we hit the region from the line and then leave the region from the right branch of the parabola. But this is not always so. Namely, starting at a lower point, we don't enter the figure from the straight line, but we enter it from the left branch of the parabola, leave from the right branch. So, since, okay, x can, okay, let me say in x direction, okay, the first curve can be, okay, the line or the parabola. So there is no first, there is no one first curve and one last curve, but there are two pieces here, which means that, okay, D is not simple with respect to x first. Okay. Well, if D is not simple, we cannot write it with respect to x first in one piece. But we can do so by dividing D into pieces. And it's clear where to divide D into pieces. Okay? We can do it as follows. Okay. Now, to make these regions simple with respect to x first, let us divide it from here. Call this D1. Call this D2. Now, clearly, D is a unino D1 and D2. Okay. And so, integral over D of f dA is integral over D1 f dA plus integral over D2 f dA from the property of the integral, double integral. But now, we look at this part. Now, concentrate on D2, D1. D1 is something as follows. It is this one like this. Okay. Clearly, in D1, you always start from the line and end at the right branch of the parabola. Okay, because we cut out the lower part. So, D1 is now simple with respect to x first. Now, if we look at D2, okay, D2 is something like this. And of course, in the x direction, you start from the left branch and leave from the right branch. Well, there are only one curve at the beginning and at the end. So this is again a simple region. With respect to x first. Okay, this means that we can transform them to iterated integrals where x comes first. Thus, integral over D f dA becomes an iterated integral with respect to x first, that is this D1 part. When we look at the D1 part, we see that we start from the line, leave from the right branch. Now, the equation of this was y is x plus 2, so that means x is y minus 1. Sorry, 2. And the right branch of the parabola, well, y is x squared, so x is square root of y. So, very simply then, we start from y minus 2 up to square root of y, okay, where these are x values now. Well, in the meantime, y changed from this level to this level, which happens to be here, okay, 4, because this is x is y squared, and this was, remember, 2, and this level is when x is minus 1, okay, so it is 1 for y. And thus, y changed from 1 to 4. Okay. Now, we are not finished, of course. This is just integral over d1. Plus, now we have to write the same thing for the second integral over d2. Well, d2 is again a simple region with respect to x first, and clearly this curve is x is, and this is a curve x is, even though they both say y is x squared, when you change to x, they differ. Here on the left branch, x is negative because this is the y-axis, okay? And on the right side, x is positive, so it is minus root y and plus root y. And thus, this becomes an integral from minus root y to root y. And y changed in the meantime. If you look at d2 now, clearly from the level 0 to the level 1. Okay. So we can still change into iterated integrals where x comes first, but if it's not a simple region, we may have to split into two pieces, as in this example. Okay. Now let us apply these arguments to calculating some volumes. Okay, now my third example. Well, let us find the volume of, okay, a pyramid. The mathematical name is tetrahedron. Okay. Bounded by the coordinate planes and the plane 2x plus y plus z is 2. Okay. Now, in finding volumes, it's always advisable to make a rough sketch. Here we can make it a very accurate sketch because this is a simple region. Everything is so simple here. We have x, y, and z. Okay. First of all, the coordinate planes zy, zx, and yx bounded from backside, from the bottom, and from the front side. Not from the top. From the top, this is the plane in question. And to sketch this plane, well, it's enough to find 3 points. Which 3 points? The easiest. 2 of them 0. What is the other one? So, if z and x are zeros, y must be 2 here. Okay, that's the y value. If the others are so, you get 1 and 1. Okay, this is z, this is x. So, the tetrahedron in question is the following. Now, this is the top of the tetrahedron. The sides are the coordinate planes. So it looks like this. It's a triangular pyramid, if you want. Now we want to calculate, okay, the volume of this. Firstly, also clear from the picture, okay, we see that the bottom of the tetrahedron is something like this, where this is 2, this is 1, this is the x-axis, and this is the y-axis. This is our D, the base of the tetrahedron. The top is just the plane given here. Well, of course, here, geometrically, it's also clear. Is that z, which is 2 minus 2x minus y, is positive on D, the base. Okay. So, volume in question is integral over D of 2 minus 2x minus y dA. Now, let us look at D more carefully. Okay. D has one corner at 2, and here it is 1. So this is D in question, which of course is a simple region with respect to x or y first. Doesn't matter. So volume, double integral df dA, can be written as, okay, the function in question, 2 minus 2x minus y. Say we write it with respect to y first. That means we look in the direction of y. So clearly, we start from the curve, y is 0, and we leave from this curve, which would be y is minus 2x and plus 1. Am I correct? When x is, 2. When x is 0, y should be 2. When x is 1, it should be 0. So this is the line equation. So y becomes minus 2x plus 2 here, and x in the meantime clearly changed from 0 to 1. Or you can write it with respect to x first. Now, if you look in the x direction here, from the left towards right, the first curve is the y-axis, which is x is 0. The last curve is x is y minus 2 over minus 2. And y changes 0 to 2. So either of them gives you the volume wanted. Okay. Now, let us consider an example from the opposite perspective. Okay, this example, or these two examples, that's fourth one. Okay, the following iterated integrals below represent double integrals. Okay. This means there is a D. There's a region, and you evaluate a double integral over D. So find, sketch D and, okay, right, sketch D and the solid whose volume is found. Okay. In the first case, we have the iterated integral 0 to 2, x over 2 to 2x, x squared plus y squared, dy dx. Now, in this example, firstly, okay, clearly the function is positive. So it represents, if it's a double integral, it represents the volume of some solid. Now, to get what it is, okay, we have to sketch D here. Well, this iteration represents a D. So how would that look like in the xy system? Well, firstly, y, that's the first variable, changed from x over 2, which is something like this, up to 2x. But we are looking in the y direction. That's important. So we start from this curve, go up to this one. And if we had a negative side, we would go downwards. Okay. So we go from this line up to the other line. Well, on the left, it could be upside down. But it's not upside down because when we look at the values of x, x changed from 0 to 2. Now, between 0 and 2, okay, from this line up to this line, and from 0 to 2, if you put them together, it says that we are working on a triangle here. Okay. So this is our D. Just a check. How would you write an iterated integral with respect to y first? You would look in this direction. First curve is x over 2. Last curve, where you leave, would be 2x, and you do it between 0 and 2. So indeed, this is the D in question. Okay. So this is a double integral. Call this I. So I is the double integral over D of x squared plus y squared dA. Hence, it's the volume. Well, what is the geometry? At the bottom, you have this triangle. At the top, you have z equal to x squared plus y squared. Well, an old acquaintance, it is a paraboloid. So very roughly speaking, okay, at the top, you have a paraboloid. At the bottom, you have a triangle. This is D. On top of this, what do you get? Remember, the paraboloid bounds the figure from the top. It means that we are not inside the paraboloid. We are below the paraboloid. So if you give some thought to this, we get the following. we have our x and y, and this is the z-axis, okay? And between x and y, we have here this side parallel to y, and this is the base. That's D. Okay. On top of it, we have the paraboloid. Okay. And the paraboloid, of course, hits the sides, and you can imagine, well, you have to use some imagination here. You should get curves here, like this. Where, okay, this thing is the, okay, this is the bounding curve, but it's the paraboloid itself. So this is the paraboloid. Okay. You can think of it as follows. Okay, you have your paraboloid. Okay, at the bottom you have a triangle. Raise the sides of the triangle, all three edges, until they hit the paraboloid. That's your figure. Okay. Well, the second one, the iterated integral in this second one is 0 to 1 minus root y to root y, and you have y minus x squared dx dy. Okay. Now again, to write down a d for these bounds in the iterated integral, we check what we have here. Okay, firstly, we are looking in the x direction. So this is the direction we look at. The first curve is x is equal to minus root y. Well, this is the same as y is x squared, but it's the negative branch. This is the negative or the left branch. Oh, the usual parabola. So it is this. This is x is minus root y. Actually, we considered this before. The other one, this is the right branch of the parabola, and so we move this way. This is x's root y. So we start from this curve, move in the right direction, hit the other branch all the time. There is nothing else. But this happens when y changes from 0 to 1. Okay. So when we put that in our picture, we have this one, and it says our d becomes this. Okay, this was the easier part of the problem. So I leave the harder part. For you to sketch. Okay, sketch the solid whose volume this double integral that is integral over d of y minus x squared dA represents. By the way, logically, of course, there is no unique such thing, but looking at the iteration, you can figure out what is meant. Okay. Now my fifth example, rather, it's not an example, but a couple of examples. Well, we said all throughout that we want to write an iterated integral with respect to y or with respect to x, and we could change one to the other by passing through the region D. So we first sketch the region D, look at it from the other side, and then rewrite an iterated integral, a new one, in the different order. Why would one change the order in an iterated integral? Okay. So why would we want to change order in an iterated integral? Well, of course, to generate questions in calculus courses is a good enough reason, but there are more serious reasons for it. Okay. Well, it may happen that the other order makes calculation easier. Namely, okay, the other order can make calculation easier. Okay. An example for that could be something as follows. Let us consider the iterated integral 0 to 1, x squared to 1 of x over 1 plus y squared dy dx. Call this I. We want to find this value. Well, we can do so. We know a lot of things about integrals. Let us calculate this one. That, obviously, that is 1 over, x is a constant because variable is y. We have 1 over 1 plus y squared. So it is nothing but x times arctangent of y. Its derivative is 1 over 1 plus y squared. And y changed from x squared to 1, which means that we have x times arctangent 1 minus x times arctangent of x squared. Well, this, of course, is x times pi over 4. Arctangent 1 is pi over 4 minus x arctangent x squared. So this integral becomes 0 to 1 pi over 4x minus x arctangent of x squared dx. Okay. Now let us look at this part first. It is an, well, you can, of course, make a substitution, say u is x squared, here is the derivative, but you still have arctangent u, which calls for integration by parts. Okay. Of course, we want to not integrate arctangent, we want to differentiate this. So f prime is x, g is arctangent x squared. So f of x would be x squared over 2. So this would be, okay, f times g, x squared over 2, arctangent of x squared, minus, okay, f times g prime, this one. Okay, all this tells us that we have x squared over 2, arctangent of x squared, minus, okay, 2's cancel out. You have x cubed divided by 1 plus x to the 4th, but that's logarithm of 1 plus x to the 4th. But you need, of course, 4x cubed, so you have to divide by that. And then eventually, you evaluate it 0 to 1. Okay. Let me use this notation. Well, that's simply then, if you have 1, you have 1/2 of pi over 4. At 0, you have 0, minus, at 0, you have 0, so you just put 1. It's logarithm 2 over 4. Okay. All in all, this becomes then pi over 4 x squared over 2 from 0 to 1. That is pi over 2 times 1/2 x squared over 2 gives you pi over 4, sorry, times 1 over 2 minus, now the inside part was this, so it is pi over 8 minus logarithm 2 over 4, which is, of course, logarithm 2 over 4. So this is the answer. Pi over 8 cancel out. Okay, this was exercise in 119. Now, let us change the order. Now, let us try after changing the order. Okay, let us recall what we had. We had y changing from x squared to 1, x from 0 to 1. So this says that y changes from x squared to 1. This is y is 1. Okay, this is x and y. And x changes from 0 to 1, of course, is here, because we have y is x squared. Now, putting everything together, okay, this gives us a d, which is this one. Okay, let us check, make a check here. When you look in the y direction, it changed from x squared to 1 and x 0 to 1. So that's what was given to us. So I is a double integral, in fact, of x over 1 plus y squared dx. Now let us write it with respect to not y first, but x first. So we look in the x direction, starts from 0 to, okay, remember x is equal to, so it is square root of y. And in the meantime, y changes from 0 to 1. Now let us calculate it this way. This is 0 to 1, okay? With respect to x, it's just x squared over 2 times, of course, 1 over 1 plus y squared. But we evaluate x from 0, x up to root y. And the remaining thing will be evaluated with respect to y. So that would give us, when x is 0, you get 0. When x is root y, you get y. So it is integral 0 to 1, 1 over 2, y over 1 plus y squared dy, which of course is 1 over 4 logarithm 1 plus y squared, 0 to 1. So it is 1 over 4 logarithm 2. Now what's the difference in these two calculations? In the previous one, we had to undergo the calculations of evaluating an integration by parts, which at the end canceled. So it was in vain. I mean, it was unnecessary calculation because it canceled with itself. What remained was just the logarithm part, and here we don't have any arctangents anywhere. We directly have the logarithm version. In other words, it made our calculation simpler. Okay. As a second example, this is a very classical one. Let us consider now the integral 0 to 1 of y to 1 of e to the minus x squared dx dy. Now, when we look at the integral and try to evaluate it directly, okay, we see that we don't know any elementary form of an antiderivative for e to the minus x squared. Okay. Well, of course, it has an antiderivative, but it's not expressible in terms of elementary functions. It's one of the monsters in calculation. So, okay, since we do not know, in fact, it's not possible to express it in this form, an elementary antiderivative for e to the minus x squared, okay, we are stuck. That is, it's impossible for us to evaluate this. Okay? So we try to change the order. This means, of course, first find the region. Okay, let us see. Well, first of all, it says that we look in the x direction, and x starts from the curve x equal to y. And we move to the right up to x equal to 1. So we move up to this. In the meantime, y changed from 1, 0 to 1. But this intersection, of course, is, because x is 1, it is 1. So indeed, this is the region in question. So this is our d. Now, let us write our integral 0 to 1, y to 1, e to the minus x squared dx dy as integral over d, e to the minus x squared dA, because it's exactly that. And now let us change the order. So we look in the y direction now. That means we look from the bottom towards top. Y changed from 0 up to y equal to x. And x changed from, as you see from there, 0 to 1. So this is 0 to 1. E to the minus x squared, it's a constant, integrating with respect to y 0 to yx dx. So it is 0 to 1, e to the minus x squared x dx, which is trivially e to the minus x squared over minus 2 from 0 to 1. Well, so it is, what do you get? For 0, you have 1/2. For 1, you have 1 over e and a 2 here. So it is this. So changing the order can make an impossible looking calculation possible.